All right, so a couple things before we get started. Math club will be Friday at 5 o'clock, and it occurs to me more than a lot of math clubs, this might be interesting to a general audience, because we're actually gonna have 3 math sciences majors who are closely related to almost all of you, that are going to talk about internship experiences. So this is something that maybe a lot of you have on your radar. The math end will take place Saturday from 10 a.m. to 5 p.m. in this building. I suggest you be there. It's a good way to kind of, get kind of juiced up for the final exams and your STEM type classes. And we will have our own separate review as well. The final exam schedule is complicated a little bit. It has to be at 5:45 here Thursday. Anybody's got a big problem back from talking to me. Okay, questions from last time. Okay, so let me, we did this last time. We had a matrix A. N by N matrix, in rows and columns. And I said, okay, this is any matrix off the tree, right? It doesn't even have to be square, right? What we noticed is ATA, when you multiply times transpose, this is an N by N matrix, right? And not only is it an N by N matrix, what other nice property does it have? Right. It's symmetric, right? So it's a symmetric matrix, so it's got all real eigenvalues. And we went through a process last time showing, so these are the eigenvectors of ATA corresponding to the eigenvalues lambda I. We went through this process last time and we showed that the length of ABI squared is lambda I times the length of BI squared. And of course, if this is orthonormal, then the length of BI squared is 1, right? So that can just disappear and you get lambda. So in fact, what we get is lambda is greater than or equal to 0. So not only is it real, for the special case where you have AT times A, in that particular type of symmetric matrix, then you get the eigenvalues are not negative, they're at least 0. We arrange the eigenvalues, we'll do this all the time. Okay, so arrange these in decreasing order. I can do this because they're real. And suppose so lambda 1 up to lambda R are the non-zero eigenvalues of we define the singular values to be the square roots of these positive matrices. Well, we can also define them to be the square roots of the 0 ones as well, but we're going to pay attention to the positive ones. So the singular values for A yeah, I can only make this in R matrix. Right. Sigma I is the square root of lambda. Whether you include zeros or not in those eigenvalues, I don't really care that much as long as you throw the matrix. Note that sigma I is the length of ABI. That's going to come up. We're going to use that in a minute. And that just basically comes from taking the square root of this equation. The length of ABI squared is lambda I. So sigma I, which is the square root of lambda I, is the length. So that's another way that you can think of the singular values are the ones that, where you have the square root above. Well, they're equal to the length of ABI. Okay, so I'm going to give you a theorem to develop, then I'm going to give you kind of the big theorem, and then I'm going to show you how to build these things. I'm not going to do really a formal proof, but I'm going to go through kind of this is how we build it, and I'm going to show you 3 minutes. So, theorem. Suppose that V1, V2, Vn is an normal basis for Rn consisting of eigenvectors of ATA. To eigenvalues um, greater than. And suppose A has exactly R non-zero singular values. So in keeping with this theorem, we will call the zero eigenvalues, if any, singular values. We want to focus on the non-zero one. Then A V1, A V2, A VR is an orthogonal basis for column R. Oops, I'm sorry, column space of A. That is to say, rank of A. Okay, so here's what we're saying. So we do our thing. We start with A, we take ATA, and we list these eigenvalues. Now, let's suppose maybe all of them are non-zero, but maybe at some point they turn into zeros. Then the ones corresponding, these are the eigenvectors corresponding to the non-zero singular values. These actually form an orthogonal basis for the column space of A. And here's why this is so. Notice that VI dot VJ is equal to 0 if I is not equal to J. Why is this true? Because at the beginning, I picked this to be an orthonormal basis. And in fact, these have rank 1 as well, if you like. So what happens when I dot AVI and AVJ? Well, this is VI transpose A transpose A VJ. And this thing right here. This is actually the transpose lambda J Bj. Why is that? Because Bj is an eigenvector for this matrix corresponding to this eigenvalue. So all I've done is I've replaced this with what it is. Right? And now this is lambda J times Vi transpose B J. And what's another name for this fancy business? Vi transpose times Bj. What's kind of more common speak for that in the parlance of our times? Dot product. It's the dot product. The dot product is 0. So that means PBI. So if BI and BJ are orthogonal, so is ABI and ABJ. So where do we go from here? Well, AB1, AB2, ABR. This is orthogonal set. So it's linearly independent. And ABR plus 1 all the way up to ABN. What do these all turn out to be? These all turn out to be 0. Because these come from the 0. These are the eigenvectors that correspond to 0 single values. These all turn out to be 0. Right. So notice if the vector y is in the column space of A, then we can write y as equal to AX for some X in Rn. This is what it means to be in column space. It means that you can write y as the matrix A times X, because basically what this X does is it expands the columns and writes y this way. And so how does this help? Well, so now let's write X as so what I've done is I've written X as a linear combination of the big I's. How do I know I can do that? I know I can do that because V1 up to Vn was an orthonormal basis for Rn, right? In fact, not only is it a basis, it's an orthonormal basis. So I'm going to do this. And notice now that this is equal to C1 V1 plus C2 A2 plus CR ABR plus CR plus 1 ABR plus 1 CN, ABN. But notice these are all zeros. Right, because so Y is in span AP1, ABR. So AB1 up to ABR is a linearly independent because it's orthogonal set that spans out of column space. And so this is exactly what we said was going to happen, that this gives us an orthogonal basis for the column space. Okay. This is going to be useful in the development of this. I'm going to tell you now what singular value decomposition is. Let me go back to my spoiler. Now I'm going to show you. I'm going to kind of build it along the way, and then I've got some numerical examples that we should try to find. Singular value decomposition, often called SVD, sounds like something you got to go to a clinic for. I think you can't say we all will, but so let's figure out what this is all about. Given any A, so suppose I pick any matrix up that I like off the street, then I can write by the way, somebody tell me what does the rank mean for A?
The dimension of the column space.
The dimension, that's exactly right. The dimension of the column space, the number of linearly independent columns. Actually, it's also the dimension of the row space, isn't it? Right? That was one of the big theorems we had earlier. So suppose we have this with rank R, then there is a matrix put this in parentheses, a diagonal matrix. I think we defined this actually earlier in class somewhere. And lambda n by n, or lambda, not a sigma, sorry, sigma n r n by n. Of the form so you kind of tuck the diagonal, you tuck the square diagonal part up in the upper left corner, and then you make the rows fit so that the whole thing is in by n. So this one is R by R. And the number of, so there should be n minus R rows here. And there should be n minus R columns. And a square diagonal up in the upper left. With these equal sigma 1, sigma 2, sigma R. So it's diagonal with the singular values on the diagonal map. And we'll, again, we arrange this way in decreasing order. That's kind of the standard. So these are the non-zero singular values in decreasing order. And orthonormal matrices U in R M by M and V in R N by N. These are both orthonormal such that due to the singular decomposition, A is equal to U sigma V transpose. And this is the famous singular value decomposition. The columns of A are sometimes called left singular vectors. Terminology. Columns of U, and this is the orthonormal matrix, are called singular vectors. The columns of V are called the right singular vectors. See, this can potentially bother me a little bit, because the columns of U are the left singular vectors. I see where that comes from. It's on the left of this sigma. But the columns of V are the right singular vector, but I don't even use V in this. So in terms of this right here, what are the right singular vectors? They're the columns of V, so what are they to V transpose? The rows. The rows. That's exactly right. Okay, so that's terminology. Here's how you build this thing, right? So given any matrix, this is a wonderful thing. You can build a matrix that's diagonal in the upper left corner, mostly zeros everywhere else, or zeros everywhere else, and then decompose it using orthonormal matrices on both sides to get A. So let's kind of go through this. Suppose this is why this works. Sigma 1, sigma 2, sigma R are positive singular values of A. So in other words, their squares are the eigenvalues of ATA. Okay. So let AI VI ATA VI is lambda I VI or lambda I and V1 of the VN orthonormal basis. For Rn. Okay, so this is just like the beginning of our discussion. ATA is an N by N matrix. We form, and it's symmetric. So we form an orthonormal basis of eigenvectors of this. Right, so here are the eigenvectors here. Here they are as an orthonormal basis. So that's kind of collecting my notation here. Notice that call AV1, AV2 of the AVR is an orthogonal basis for the column space A. Right, that's just what we proved, that these things here, when you take the eigenvectors that correspond to the positive singular values, they make and apply A to the VIs, they make an orthogonal basis for the column space of A. So now, let's let. I'm going to define. The vector UI to equal 1 over the length of AVI. By the way, anybody, I mean, what am I sort of doing here? So those AVIs here, they form an orthogonal basis. What are you suppose I'm trying to do with these U's? What's going on here? I'm making it orthonormal. Everybody agree with that? Because I'm taking these orthonormal AVIs and I divide out by length, so this is going to make them all unit vectors. So really what I'm trying to accomplish here is I'm just trying to turn this orthogonal basis into one that's orthonormal, right? There's another cool name for AVI. Anybody remember what that is? What's the length of AVI? I'll remember from last time. Yeah, there's a lot of information there. I get it. Remember how the singular value was the length of AVI, right? So in particular, UI is 1 over sigma I AVI, or if you like, sigma I UI is VI, and U1 to UR is orthonormal. So, now notice I've got me some matrices. I know how to build sigma already because I've got the singular values. And this is my instruction book. Fit a diagonal matrix in here with the non-singular values, fill the rest up with zeros, make it m by n. Agree? I can build the sigma now, right? How big does U have to be? This has to be m by n, and this has to be n by n. Now, see, I'm thinking I can build with V, and I hope that my notation is suggestive, because I can just make these vectors somebody's columns, right? They're already orthonormal. I agree. So that's what's coming. This is either going to be V with V transpose. I need something else to build the U's. Look at me. I've got me some orthonormal columns here, but there's something amiss on this one, or potentially amiss. What's wrong with my set orthonormal there? If I'm going to try to use it to build an m by m matrix, I may not have enough, right? Can I fix this? R is less than or equal to M, right? R is the rank of the columns, or is the rank of the matrix A. It's less than or equal to M. What if it's less than? How can I get M out of my R in the spirit of what we've been doing before? There you go. So let's expand to just make it grow. Add as many as you need. Well, of course, you can add more than him, or he can go past him, I should say. So just use the Gram-Schmidt. Make this, if necessary. Now, of course, this might be M already, in which case you win. There's no other work to be done. Now, to show you that this works, I'll kind of sketch this and then we'll do get our hands dirty and do some real world examples here. Okay, build a matrix U like I kind of thought I would out of that orthonormal basis for RM. Let's let V equal V1, V2, Vn. Lucky for us, we already started with an orthonormal basis, so there wasn't anything else we had to do. Now look at AV. This is A V1, A V2, A V1. These are the columns, right? Which, let me point out, is A V1 of the A VR, and then 0 columns from here on out. Because remember, if you have some zeros behind it, you just get 0 right? So this is what AV is going to look like. On the other hand, let's look at U sigma. So U is U1, U2, UM, and sigma I'm going to try to write down. This is sigma 1, sigma 2, sigma R, zeros, 0, 0, and zeros off the diagonal. Now, if I multiply this out, these columns times this, then what I get is sigma 1, U1, sigma 2, U2, sigma R, UR, and the rest zeros. See, let me point out that each one of these was sigma. This was sigma 1, U1. This was sigma 2, U2, and this was well, I should do it down here, shouldn't I? Sigma 1, U1, sigma R, UR. Notice this matrix, because these match this and zeros match, is equal to A and B. So at the end of the day, what I've gotten is U sigma is equal to A and B. Now multiply on the right-hand side by V transpose. You get the identity here. So you get U sigma V transpose. So this works. Okay, so let's actually do an example where from scratch we'll kind of get everything that we can. Okay, so I'll show you how the process works. Any questions before we start? Okay, so let's just build up one from ground zero. Suppose that I give you this matrix and I say, okay, find me the singular value decomposition. So A is equal to 1 minus 1, 1, 2, 1, 1. Right, so this is a nice wholesome 3 by 2 matrix. It's not square, so we're going to do something about that. A transpose is 1 minus 1, 1, and 2, 1, 1. And so A transpose A, well, let's see, it's this row times this column, so it's going to be 1, 2, 3. This row times this column is going to be 2 minus 1 is 1 and 2. This row now, this column is 2 minus 1 is 1, get 2. And that gives me 4, 5, 6. And get the same thing. Now, here, what's a good gut check at this point? I think one of the important skills to develop as an engineer or scientist is along the way, think, is this developing right? Does it make sense? And I see something about this that tells me, hey, I'm probably on the right track. It's a symmetric matrix. That's what it's supposed to be. Okay, so that's good. That's at least there's promise that I haven't screwed it up yet. So what do we need to do first? Well, we need an orthogonal basis of eigenvectors of this matrix. Now, what I need to do actually is to try to diagonalize this really. So let's look at the determinant of 3 minus x, 2, 6 minus x. And this gives me x squared minus 9x. And 18 minus 4 is 4. Get that. So I get eigenvalues. Notice that no number is 0 in this particular case. But, okay. So I need the singular values, right? That's another good gut check at this point. Notice that I got all eigenvalues that were, none of my eigenvalues were negative. So that's a good kind of gut check. This is going well. So what are my singular values? Looks like. And notice, you know, this is really kind of silly, but you should stick with actually the standard thing. You want to do this in decreasing order of size, right? Because that's what it calls for. Just the correct nomenclature, if you will. So I can already build my sigma. And I can already build my V too. But let's start with the sigma. I don't know much, but it's got to be 3 by 2. Because it's got to match the size of the original matrix A. So what are my entries? There's a diagonal piece up here. And once I diagonal down my singular values, that's it, baby. I mean, the rest of them have to be 0. There you go. Okay, so it's fine. And I can find, well, actually, so there's sigma. Let's find the V now. So how do I find V?
The eigenspace.
That's right. We need to remember the V's, the columns that come from an orthonormal basis of eigenvectors that this should have. So I need to find the eigenvectors, as you say. So my question now is V. So lambda equals 7. I have, let's see, minus 4, 2. 2 minus 1. I'm looking for the null space of that. Notice that the top row is multiple of the bottom row, as it should be. And so this as 2 minus 1. And so I can let V1 be, well, so. Let's say the dot products or the dot products with both rows is equal, so that'll work. I agree. And so what do I want B1 to be? Root 5, yeah. But remember, it's normal basis. Lambda equals whatever the other one was, 2. I get 1, 2, 2, 4. So I have an eigenvector, so I can do this as 2 minus 1. Notice, by the way, these two are orthogonal, as they should be. That's another gut check. Right? And I get V2 is equal to 2 over radical 5, 1 over radical 5. So let's might as well collect it here. Right, okay, so far. Okay. Now, how about you? Well, I'm gonna have to go back to this earlier equation here. So here's where we get our U's. And our quest for U1 vector is 1 over sigma 1, A V1. You know, I really should have done also. Hopefully everybody's got this up here. I'm gonna write A down again. So U1 is this. So what is U1 in this case? This is 1 over radical 7 times A V1. And what was V1? It was 1 over radical 5, 2 over radical 5. Now this should give me a 3 vector, 1 over radical, or 3 by 1 vector. This is 1 and 2. This is 5 over radical 5. This is 1 over radical 5. And this is 3 over radical 5. Now I want these to be orthonormal too, right? Let me actually rescale this. Oh, yeah, this is already orthonormal, I guess. So I get 5 over radical 35, 1 over radical 35, and 3 over radical 35. 25, yeah. There's U1. How about U2? U2 should be 1 over sigma 2, AV2, which is 1 over radical 2, 1 minus 1, 1, 2, 1, 1, times the vector, 2 over radical 5, minus 1 over radical 5, my V2. And so this is 1 over radical 2 times the 3 vector, 0, minus 3 over radical 5, I bet it's a one over radical 5. And this is 0 minus 3 of radical 10, 1 over radical 10. So here's you so far. It should be corresponding to first one 5 over radical 35, 1 over radical 35, 3 over radical 35, 0 minus 3 over radical 10, 1 over radical 10. And now I've run out of room. I need another column. Oh dear, whatever shot it is.
Graham Schmidt.
Right. I've got another idea though. We need to, this is just like the problem we talked about in the proof. We're short one, right? What do? We can expand this to a basis of R3. We could Graham Schmidt. Who wants to Graham Schmidt? Nobody. Well, let me point out, let me rescale these vectors, right? So let me kind of do this quickly. This first vector is 5, 1, 3. I mean, screw the radical 35, right? Just scale it. Right? The second vector is 0 minus 3, 1. Correct? Notice that these two vectors are orthogonal. All you need to do is find a third vector, A, B, C, that is orthogonal to both of them. Right? They're already, so just find and then scale it. And so to be orthogonal to the first one, you get 5A plus B plus 3C is 0, because the dot product here has to be 0. And you also get this auxiliary equation minus 3B plus C is equal to 0. And you can solve this, and a solution that I got was 513,031. I got A equals minus 2, B equals 1, and C equals 3, I guess. If that works. Minus 10. Yeah, that looks like it works. And so this vector you can get is minus 2, 1, 3. Well, what do I have to do with that? I need to make it normal now, right? So this is going to be what, 9, 14. So make it like minus 2 radical 14, 1 over radical 14, and 3 over radical 14. So there I go, minus 2 over radical 14, 1 over radical 14, 3 over radical 14. And that should be, this should be my view. Okay, any questions on that? So let me give you two exercises. Number one, check A is equal to U sigma in transpose. Right. And number two, work the same problem I did, but now instead of starting with A, remember we had A was 3 by 2. Do the transpose of it, do the 2 by 3 matrix, it's a transpose, and see what you come up with. There should be familiar things coming up, and I think this will be kind of good practice. Okay, any questions? Tomorrow, Friday, last day of class, we will have questions. Anything's game. We should probably hit this up first if you've got any serious questions about that. But like I said, anything's game. So bring questions and don't forget to do your evaluations and and do the response evaluation. Well, final. Oh, and also the last week of class, I will be having office hours, but I'll announce them on Friday. So see you all next time.